Section: Introduction. In this section, we delve into how we can extract detailed information about large language models, LLMs, using common API configurations. By analyzing the low-rank output layer present in most LLM architectures, we can identify a restricted output space called the LLM's image. This image can be obtained by collecting a small number of LLM outputs. Our innovative algorithms enable us to do this efficiently for standard LLM APIs. Understanding the LLM image opens up various possibilities for different applications. For example, we can determine the embedding size of an API-based LLM and even use LLM images as unique signatures to identify model outputs accurately. These signatures are sensitive to even minor changes in the LLM parameters, making them useful for inferring detailed information about model updates. Despite the potential security implications of revealing LLM images, there is no straightforward solution to prevent their extraction without significantly altering the LLM architecture. While providers may consider hiding this information, features related to the API have essential and safe uses for LLM clients. Our methods serve as a reminder for LLM providers to carefully consider the impact of their model architectures and APIs. However, we see these methods as a valuable tool that providers can choose to maintain trust with their customers by allowing external audits of their models. Section Summary. In this section, we demonstrate how to extract detailed information about large language models, LLMs, using common API configurations. By exploiting the low-rank output layer common to most LLM architectures, we can obtain the LLM's image, allowing us to track model changes, recover hidden prompts, and obtain full vocabulary outputs. Our method enables LLM clients to hold providers accountable, establish unique model identities, and identify outputs with high accuracy, ultimately enhancing trust and accountability in API-protected LLMs. Section: Fast, Full Outputs from API-Protected LLMs. In this section, we present an algorithm for obtaining fast and complete outputs from API-protected large language models, LLMs. While most LLM APIs do not provide full outputs, we aim to recover these outputs by leveraging a common API feature that allows users to bias the logits for specific tokens. The algorithm we propose requires 43 API calls to obtain one full output accurately. We introduce an enhancement that theoretically achieves full outputs in 45 API calls for APIs that offer the log probability of the top tokens. However, this improved algorithm faces numerical instability issues. To address this, we develop a numerically stable algorithm that can retrieve full outputs in 47 API calls. Furthermore, we devise a practical algorithm to handle stochastic APIs that randomly select outputs from a set of possibilities. This algorithm enables us to gather complete outputs in less than 49 API calls on average. By incorporating a preprocessing step to identify the low-dimensional representation of the LLM, we reduce the number of API calls in all the algorithms from 50 to 18. This acceleration significantly speeds up the process of obtaining full LLM outputs, making it up to 100 times faster and more cost-effective, depending on the specific LLM. Our objective is to extract a comprehensive next token distribution from an API-protected LLM. Assuming the API allows conditioning on a prompt, specifying up to 46 tokens, and adding a bias term to the logits before applying the softmax function, we can retrieve the top probable tokens and their probabilities from the biased distribution. By querying the API with maximally biased tokens, we can obtain the biased probabilities, from which we can derive the unbiased probabilities for each token. This approach enables us to acquire the full distribution in 45 API calls. To address numerical instability in the algorithm due to exponential growth and approaching terms, we propose a strategy to calculate unbiased probabilities more stably, albeit at a slightly slower pace. By querying the API with maximum bias on specific tokens, we can determine the unbiased probabilities and obtain the complete output in 47 API calls. Additionally, we tackle stochastic APIs, such as OpenAI's LLM APIs, which introduce randomness in the outputs. We model this stochastic behavior as a collection of potential outputs, from which the API randomly selects. By biasing only certain tokens in each call, we can identify the output the API returns from and collect the full set of probabilities after an average of 49 API calls. Section Summary. In this section, we present an algorithm to efficiently retrieve full outputs from API-protected large language models, LLMs, by leveraging a common API option that allows users to bias token logits. Our algorithm significantly reduces the number of API calls needed to obtain complete outputs, making the process faster and more cost-effective. Additionally, we address numerical instability issues and provide a practical solution for dealing with stochastic APIs, enabling the collection of full LLM outputs in a more efficient manner. Section: Ultra-fast full outputs using the LLM image. In this section, we present a method that allows us to quickly obtain full outputs using the LLM image. The main factor affecting the runtime of each algorithm has been the dimensionality of the LLM output space. By introducing a preprocessing step that leverages the low-dimensional LLM output space, we can generate compact versions of various algorithms. This preprocessing step can lead to significant speed improvements, depending on the specific LLM being used. The key idea behind this algorithm is that just 5 linearly independent outputs from the API form a basis for the entire output space, given that the LLM's image has a dimension of 5. By collecting these outputs as a preprocessing step using any of the algorithms and 5 unique prompts, we can reconstruct the full LLM output after only 18 queries for each subsequent output. This process involves using the additive log ratio, ALR, transform to manipulate the columns of the output matrix. To determine the embedding size of API-protected LLMs without detailed architectural information, we can collect linearly independent outputs from the LLM to form a basis for the LLM's image. By observing the singular values of the resulting output matrix, we can identify the embedding size of the model. This method has been validated on various LLMs, including a popular API-protected model, GPT-3.5 Turbo, where we estimated the embedding size to be around 4,600 to 4,650. Monitoring changes in the embedding size and parameter count of LLMs over time can be crucial, and our method provides a way to track such updates effectively. Section Summary. In this section, we introduce a preprocessing step that leverages the low-dimensional LLM output space to significantly speed up various algorithms, with potential speedups of multiple orders of magnitude depending on the LLM used. By collecting linearly independent outputs from the API as a preprocessing step, we can reconstruct the full LLM output with only a few queries, making methods relying on full model outputs much more cost-effective. Additionally, we demonstrate a method to infer the embedding size of API-protected LLMs solely from their outputs, enabling us to monitor changes in model architecture over time, such as updates to the embedding size and parameter count. Section: Identifying LLMs from a single output. In this section, we identified LLMs from a single output. We observed that the images of 2 different LLMs, even different checkpoints from the same LLM, are mostly separate. For example, the logit output from a late training checkpoint of Pythia 70M only lies in the image of that specific checkpoint, not in the images of the checkpoints before or after it. We also confirmed that this output does not fall within the images of any checkpoints from a similar LLM trained on deduplicated data or any checkpoint from a larger LLM trained on the same data. This indicates that a small change in parameters can greatly affect the image of an LLM. Essentially, the dimension of the intersection of 2 LLMs images is small, making it possible to determine which LLM produced a specific output without knowing the exact inputs. This unique image of the model serves as a signature, allowing for model identification. This discovery has implications for holding LLM providers accountable. For instance, if one provider suspects another of stealing their model, they can compare the model signatures to verify. Similarly, if an auditor needs to check if a provider is falsely claiming to use a proprietary model, they can do so by examining the LLM signature. Furthermore, we discussed how sensitive LLM images can help detect minor and major updates to API-protected LLMs. By analyzing changes in the LLM image, we can distinguish between different types of updates, such as partial updates where the model changes but the softmax matrix remains the same. This information is valuable for monitoring unexpected changes in API LLMs. Additionally, we speculated on the possibility of detecting LoRa updates, a parameter-efficient fine-tuning method, by analyzing LLM outputs before and after the update. By decomposing these outputs, we may be able to identify low-rank updates in the model weights. This could provide more detailed information on certain types of LLM updates. Access to the LLM's image opens up various capabilities, including identifying unargmaxable tokens, which are tokens that the model cannot output due to constraints. Our method can identify these tokens using only the LLM's image, without needing full access to the softmax matrix. This ability allows API customers to uncover peculiarities in LLM behavior, such as tokens that the model struggles to output under greedy decoding. Section Summary. In this section, we demonstrate that the image of a large language model, LLM, is distinct for different models or even different checkpoints of the same model. By analyzing the logit outputs, we show that the image of an LLM is highly sensitive to small parameter changes, allowing for precise identification of which LLM produced a specific output without knowing the exact inputs. This sensitivity can be leveraged to detect minor and major updates in LLMs, such as through the detection of LoRa updates, and has implications for LLM provider accountability and monitoring unannounced changes in API-protected LLMs. Section: Recovering the softmax matrix from outputs. In this section, we explore how we can recover the softmax matrix from outputs. Our method allows us to access the image of the output layer, rather than the output layer parameters. We investigate ways to reconstruct the output layer parameters, either exactly or approximately. We believe that the LLM embeddings are typically located near the surface of a hypersphere with a small radius. This is supported by the observation that the Pythia LLM embedding norms are small and follow a roughly normal distribution. Assuming this pattern holds for any LLM, we can try to recover the parameters by enforcing a constraint that all embeddings must have a magnitude of 1. To find the matrix of model logits, we can determine the parameters, up to a rotation, by decomposing a matrix such that a specific condition is satisfied for all elements. This solution can also be approximated by performing a singular value decomposition, although the magnitudes of the rows may be less than a certain value and may not follow a normal distribution. Regarding the improved LLM inversion, a recent method focuses on recovering hidden prompts by training an inversion model using the full LLM API outputs. We suggest a modification to this approach to address the vocabulary size mismatch between the LLM and the inversion model. By leveraging our understanding of the LLM's image, we can obtain a more suitable representation for the inversion model, which can then be processed further using an MLP. Additionally, we discuss basis-aware sampling, which aims to avoid certain sampling errors by identifying tokens with non-zero true probabilities. This method relies on knowing the basis of the LLM's output space, making it applicable only to LLMs with known images. Our proposed approach enables this decoding algorithm for API-protected LLMs. We also consider potential mitigations that LLM providers could implement to protect against our methods. These include restricting API access to logprobs or logit bias, or transitioning to LLM architectures without a softmax bottleneck. Each proposal has its advantages and challenges, with the choice depending on the trade-offs between security and usability. Section Summary. In this section, we explore methods to recover the softmax matrix from LLM outputs. By assuming that LLM embeddings lie near a hypersphere surface with small radii, we can attempt to reconstruct the output layer parameters by enforcing a constraint that all embeddings must have a magnitude of 1. Additionally, we propose an improved LLM inversion technique that leverages knowledge of the LLM's image to generate a linearly lossless representation for the inversion model, enabling more efficient decoding algorithms while considering mitigations that LLM providers can implement to safeguard against such methods. Section: Discussion. In this section, we will discuss the potential applications of our methods and their impact on building trust between LLM API users and providers. Our methods are not harmful to LLM providers. For example, we can determine the embedding size of the LLM, which is usually not publicly available in proprietary LLMs. However, knowing this information does not allow a competitor to fully uncover the LLM's softmax matrix parameters or enhance their own model's performance significantly. Other factors like training data mix, human feedback, and engineering choices remain crucial and undisclosed. Even if someone tries to use model outputs to extract hidden prompts, it is unlikely to cause harm because hidden prompt leakage is a known vulnerability. It is recommended that no private information should be included in these system prompts. The main risk of our findings is that model stealing methods relying on full outputs become more affordable, which could impact models like GPT 3.5 Turbo. On the positive side, enabling LLM API users to detect model changes fosters trust between providers and customers, promoting greater accountability and transparency. Our method allows for efficient model auditing protocols without revealing model parameters or detailed configurations, enhancing model safety and privacy for personalized, proprietary models. We believe that our methods do not require a change in LLM API best practices but offer additional tools for API customers while alerting LLM providers about the information their APIs expose. In a fascinating case of simultaneous discovery, another group proposed a similar approach to ours for gaining insights into API-protected LLMs. We compare our work with theirs, noting differences in algorithms for obtaining full outputs and improvements in methods for accessing API outputs efficiently. Our experiments with OpenAI's API encountered stochasticity issues, leading us to develop a stochastically robust full output algorithm. Our colleagues seem to have a more stable API endpoint, avoiding such problems. Lastly, our focus on understanding the capabilities of attacks post-LLM acquisition complements their emphasis on defenses and mitigations against attacks. Together, our work provides motivation for implementing defenses based on the insights gained from LLM images.